we're going to relate our angular properties to our translational properties. If we have here angular displacement uh, is going to be equal to the arc length around the axis of rotation divided by the radius. So what that means is if you have your arc length, that's going to be equal to your angular displacement, or what degree this rotates with, times your radius. Let's pretend our arc length is an entire circle. The entire circle is the circumference. The circumference, we went all the way around, that would be the circumference. The arc length would be the circumference. What would our angular displacement be? 2 pi times the radius. So this formula is how we relate translational to angular properties. Now, what we use if we're going to decide that this is going to go in a linear fashion instead of using the arc length, we can also similarly say if we, cut this wheel and spread it out in a linear fashion, we'd have our displacement would be equal to our angular displacement times radius. So this formula is essentially saying the same thing as this formula, but let's put it into terms that we're used to working with. And the displacement, if we want to know how far something displaces based on how how much its angular displacement is, and we know the radius from the axis, and then we can figure out how far it's going to go. Similarly, we can take this and understand that if we have this formula, we can relate that. We know that that is change in velocity over time, and we know this is change in angular speed times radius. Times would cancel out, and how do we get velocity? How do we relate velocity? The same way. So we have a way to relate velocity, we have a way to relate displacement, and if we did the same exercise with acceleration, we could relate acceleration the same way. These three formulas relate our translational properties and our rotational properties. Our equations for constant angular acceleration are going to be very similar to our equations for constant acceleration, constant translational acceleration. Here they are. Your angular velocity, final angular velocity equals initial angular velocity plus angular acceleration times time. Angular displacement equals 1/2 final final angular velocity plus initial angular velocity times time. Angular displacement is angular velocity initial times time plus 1/2 angular acceleration times time squared. Angular velocity squared, final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times angular displacement. If you look at these, they're very similar to equations of constant translational acceleration. They are they work the same way. These two. So you know, if you recall how to use these equations, you're going to use these equations the same way when we deal with rotational motion. And understand, if I can figure out an aspect of rotational motion, say the angular displacement, once I have that angular displacement, I can now plug that in for my, or I can solve for my translational displacement by multiplying by the radius, as we showed before, as what was shown over here. If we have a top spinning at a rate of 175 revolutions per minute, and it comes to rest after 1.3 minutes, how many revolutions does the top undergo? So what we have here is our angular speed and our time. So what's our angular speed? Initially, it's 175. Now that's revolutions per minute. We got to change that to radians per second. So multiply by 2 pi radians over 60 seconds. That's a 60 seconds. And we get 18.3 radians per second. Our time is 1.3 minutes. We'll convert that to seconds by multiplying by 60. That's 78 seconds. We know our final angular speed is going to be 0 because it comes to rest. And we want to know how many revolutions does it undergo. So essentially we can find our angular displacement, and we can figure out how many revolutions that is. Using the second formula, plugging in our numbers, we'd have 18.3 plugged in here plus 0, multiplied by 78 seconds to get our angular displacement. That's 714 radians. They do want to know how many revolutions it undergoes. So if we convert that to revolutions, if we convert that back to revolutions, we would get 114 revolutions. We're just dividing it by 2 pi. So that's really the answer. That's what it would be. That would be the answer in the correct units. They want to know revolutions. Could you have solved this by not converting? Sure, absolutely. That would have been simple. But you would have had to convert anyway to figure out the angular acceleration of the top. So if we want to figure out what the angular acceleration is, well, now I know, 4 properties of angular kinematics. Therefore, I can use any equation I want to find angular acceleration. Let's use the easiest one. Initial angular velocity, final angular velocity is equal to initial plus angular acceleration times time. So this is 18.3. This is what we're looking for. Time, 78 seconds. And this is 0. And we solve and get our angular acceleration is negative 0.235 radians per second squared. Why is it negative? Well, let's look at a top view of our top. That's our top spinning around, and we are saying that it's spinning with a positive angular velocity to start. Okay, so our angular velocity is this way, and our angular displacement is also this way, which is counterclockwise positive, well, our angular acceleration is negative. Why is it negative? This thing is slowing down and stopping. So angular acceleration is acting in the opposite direction of the other two.